Welcome to this lesson on chemical bonding and structure for IB Chemistry Higher Level. In this lesson, we will cover ionic bonding, covalent bonding, metallic bonding, intermolecular forces, bond polarity, resonance, hybridization, and the relationship between structure and properties. Ionic bonding occurs when electrons are transferred from metal to non-metal atoms, forming oppositely charged ions held together by electrostatic forces. The resulting ionic compounds have high melting and boiling points due to the strong attractions between ions. They conduct electricity when molten or dissolved in water, but not when solid. Ionic compounds are typically soluble in water, but not in organic solvents. Examples include sodium chloride, magnesium oxide, and calcium fluoride. The strength of an ionic bond depends on the charge on the ions and the distance between them, as described by Coulomb's law. Covalent bonding occurs when atoms share electrons to achieve a stable octet. A single bond involves one shared pair of electrons, represented by one line. A double bond involves two shared pairs, represented by two lines. A triple bond involves three shared pairs, represented by three lines. Electronegativity is a measure of an atom's ability to attract shared electrons in a chemical bond. The Pauling scale is commonly used, with fluorine being the most electronegative at 3.98 and francium the least at 0.7. The difference in electronegativity determines bond type. 0 to 0.4 indicates non-polar covalent bonds. 0.5 to 1.7 indicates polar covalent bonds. Greater than 1.7 indicates ionic character. For example, hydrogen fluoride has a difference of 1.9, making it highly polar. Water has polar covalent bonds, with oxygen being partially negative and hydrogen partially positive. The valence shell electron pair repulsion theory predicts molecular shapes based on electron pair repulsions. Electron domains around a central atom repel each other and arrange to minimize repulsion. Two electron domains give linear geometry with bond angle 180 degrees. 3 give trigonal planar with 120 degrees. 4 give tetrahedral with 109.5 degrees. 5 give trigonal bipyramidal with 90 and 120 degrees. 6 give octahedral with 90 degrees. Lone pairs occupy more space than bonding pairs, so they reduce bond angles. For example, water has tetrahedral electron geometry, but bent molecular geometry due to two lone pairs. Hybridization explains the bonding in molecules by mixing atomic orbitals to form hybrid orbitals. In sp hybridization, one s orbital mixes with one p orbital, forming two sp hybrid orbitals with linear geometry. In sp2 hybridization, one s mixes with 2p, forming three sp2 hybrids with trigonal planar geometry. In sp3 hybridization, one s mixes with 3p, forming four sp3 hybrids with tetrahedral geometry. sp3d and sp3d2 hybridization explain the shapes of molecules with expanded octets. Hybridization helps explain bond angles and the existence of double and triple bonds in molecular orbital theory. Metallic bonding occurs in metals where electrons are delocalized in a sea of electrons. Positive metal ions are embedded in this electron sea and are held together by attraction to the delocalized electrons. This explains the characteristic properties of metals. High electrical conductivity, because electrons can move freely. High thermal conductivity, malleability and ductility, and high melting points. The strength of metallic bonding depends on the number of delocalized electrons and the size of the metal ions. Transition metals have high melting points due to additional d-electron bonding. Intermolecular forces are attractions between molecules weaker than covalent bonds. London dispersion forces occur in all molecules due to temporary electron fluctuations, creating temporary dipoles. They increase with molecular size and number of electrons. Dipole-dipole forces occur between polar molecules with permanent dipoles. Hydrogen bonding is a special dipole-dipole when hydrogen bonds to highly electronegative fluorine, oxygen, or nitrogen. It is the strongest intermolecular force and explains water's unique properties. Ion dipole forces occur between ions and polar molecules, important in solubility. The type of bonding and structure determines physical properties. Ionic compounds have high melting points, conduct when molten, and dissolve in water. Covalent molecular compounds have low melting points and do not conduct. Covalent network compounds like diamond and silicon dioxide have very high melting points. Metallic compounds conduct and are malleable. Solubility follows the principle like dissolves, like polar substances dissolve polar substances, non-polar dissolve non-polar. Hydrogen bonding in water explains its high boiling point, surface tension, and ice floating. Resonance occurs when a molecule can be represented by two or more valid Lewis structures that differ only in electron arrangement. The actual structure is a hybrid of all resonance forms. For example, the carbonate ion has 3 equivalent resonance structures. Ozone has 2 resonance structures. Benzene has 2 resonance forms with alternating double bonds, but in reality has equal bond lengths between all carbons due to delocalization. Delocalization, where electrons are spread over multiple atoms, increases stability. The resonance energy is the difference between the experimental bond energy and the theoretical value from a single Lewis structure. Let's try some practice questions. Question 1. Explain why sodium chloride has a higher melting point than hydrogen chloride. Question 2. Predict the shape and bond angle of ammonia using VSEPR theory. Question 3. Describe the type of intermolecular forces in water and explain why ice floats on water. Question 4. Explain the difference between sigma and pi bonds. These questions cover the key concepts in this topic. To summarize the key points of this lesson, first, ionic bonding involves electron transfer and forms compounds with high melting points. Second, covalent bonding involves electron sharing and can produce polar or non-polar bonds. Third, VSEPR theory predicts molecular shapes based on electron pair repulsions. Fourth, hybridization explains bonding in molecules with multiple bonds. Fifth, intermolecular forces determine physical properties. Sixth, London dispersion forces, dipole-dipole, and hydrogen bonding are the 3 main types of intermolecular forces. Remember to practice past paper questions to master this topic. Thank you for watching this lesson on chemical bonding and structure.